Hello and welcome to today's lecture on MOS transistors. This is the first lectures on this topic. As I mentioned in the last lecture, our course will be based on CMOS circuits, because CMOS is the technology of choice today, and we shall follow a bottom up approach. In the bottom up approach, as you know, we start with very simple things, and we shall start with MOS transistors, and then we shall gradually discuss MOS inverters, MOS complicated circuits and other things. And so, today is the first lecture on MOS transistors, and here is the agenda of today's lecture. After giving a brief introduction, I shall discuss structure of MOS transistors. You will see there are different types of MOS transistors available, and I shall discuss all of them one after the other. And then I shall discuss fabrication steps of CMOS transistors, because this understanding of this fabrication step is necessary to know about how actually CMOS circuits are realized, and then what are the complications and steps involved in it. Okay. As you know, the base semiconductor material used for the fabrication of MOS integrated circuits is silicon. Silicon is a material which is available in abundance in nature, and it is very cheap. So, there is no dearth of raw material. In the nature you get plentiful of silicon in the form of silicon dioxide or sand. However, you have to use a very purified form of silicon for the fabrication of VLSI circuits. So, usually by reacting silicon dioxide or sand with carbon, the silicon is purified to a great extent, then it is used for the purpose of fabrication of VLSI circuits. And here we shall be using the term MOS. What do you really mean by MOS? A MOS stands for metal oxide semiconductor. You will see these transistors are realized by using three different types of material. One is metal. Metal is usually aluminum, or sometime polysilicon is also used for the purpose of conducting material. And oxide is your silicon dioxide, which is used as an insulating layer, and semiconductor is silicon with impurity. As you know, silicon in the pure form is not a conductor, is an insulator. However, you have to add some impurity to to make it semiconductor. That means, it will be partially conducting. And then you will be creating pattern layers of three conducting materials. The conducting materials are metal in the form of aluminum, and then polysilicon, which is also a conducting material, which is used for making interconnections among different parts of the circuit. Then diffusion is also a conducting layer, which will be created by usually two processes. One process is known as diffusion, another is ion implantation. Then these three layers are actually realized one after the other using silicon dioxide as an interfering layer in the form of a sandwich. So, the sandwich like structure of is realized to implement MOS transistors, and we shall see the fabrication of MOS transistors involve a series of photolithographic techniques and chemical processes involving oxidation of silicon to realize silicon dioxide, diffusion of impurities into the silicon to implement N plus or P plus regions, and deposition and etching of aluminum, that means which is used for the purpose of interconnecting different layers. So, etching of aluminum, polysilicon on poly on silicon to provide interconnection. So, with this brief introduction, let us have a look at the structure of a MOS transistor. So, as you can see, this simplified diagram of a MOS structure which is shown here, it has got two two regions. This is the substrate. This substrate is either lightly doped p type or n type. Here I have not shown anything, but it can be either p type, lightly doped p type or lightly doped n type. And then you have got, you will be creating the two highly doped regions, islands you can say, which are known as source and drain. So, on a lightly doped structure substrate of silicon, two islands of diffusion regions called source and drain, and this source and drain which are heavily doped are of opposite polarity of that of the substrate. So, that means, if the substrate is lightly doped p type, then these diffusion regions, that means source and drain, will be of n type, n plus type, and these are known as source and drain, as you can see here. And of course, for taking interconnection, you can see metal layer has been deposited for interconnecting to other parts of the circuit. Then between these two islands, source and drain, a thin insulating layer of silicon dioxide is formed. You can see this is the thin layer of silicon dioxide, which is also known as thinox, thin layer of silicon dioxide. And on top of this, a conducting material made of polysilicon. This is the polysilicon layer which has been deposited on this thin layer of silicon dioxide, and then on top of the polysilicon you can deposit metal for making interconnections, and this forms the gate. That means, on top of the polysilicon the metal layer is deposited and this forms the gate. Now, this is the structure, generalized structure of a MOS transistors, and as I told, you have two alternatives. You can have either a p type substrate or a n type substrate. So, whenever you are using p type substrate and these heavily doped regions are n type, called n plus and n plus, then we realize a NMOS transistor. Now, the MOS transistor operation is based on the flow of current in this channel region, which is under this silicon dioxide layer. This is the channel region, this flow of current between source and drain in this channel region. Now, you see, in this form, in this original form, there cannot be any flow of current, because flow of current requires some carrier. So, in absence of any carrier, there cannot be any flow of current. So, you have to create some carrier, charge carrier, so that current can flow in this channel region. And for that purpose, there are two different techniques are used. One is known as enhancement mode. In this mode, what is being done? A positive voltage is applied on the gate, and whenever a positive voltage is applied on the gate, it will induce charge of opposite polarity on the other side of the silicon dioxide. So, in this region, in this channel region, charge of opposite polarity will be induced, or in other words, an inversion layer is created. So, that inversion layer is made of electrons in this particular case, and then electrons forms the channel. I mean, the channel in this region, that electrons can be used to carry current between source and drain. Since in this particular case you are applying a voltage to create the channel, that means you are creating an inversion layer, and by controlling the gate voltage, the flow of current between the source and drain is carried out, and that is the reason why it is called NMOS enhancement type transistor. So, in this particular case, originally there is no charge carrier, but you are applying a positive voltage of sufficiently high positive voltage to create charge of opposite polarity, in this particular case electron, for the flow of current between source and drain. Now, is it the only way of creating the conducting path? Another alternative is there, in which case by you can create the channel region, you can actually you can implement by using ion implantation, you can create electrons, you can put electrons in this region. That means, in the absence of any gate voltage, a channel is formed and electrons are available in this region, and as a consequence, even when the gate voltage is 0, current can flow between source and drain. And you may say that in this particular case, how do you really stop the flow of current? What you can do, you can apply a negative voltage to the gate, and obviously, if you keep on increasing the negative voltage on the gate, then it will gradually deplete this region, that means replace the region from the charge carriers. That means, the electrons which have been deposited here will be removed whenever a negative voltage is applied, and that will induce holes, and holes will actually remove these electrons. So, here also, that means, by applying a negative voltage starting from 0 to some negative voltage, you can control the flow of current between the source and drain. So, thus you have realized a NMOS depletion type transistor. So, basic structure remaining same, except you are here at the time of fabrication, you are creating the channel region by diffusion process. Then let us come to the third alternative, where you are starting with a N type substrate. That means, this is a lightly doped substrate, and then in this case these heavily doped regions will be of P type. That means, here it will be P plus and P plus, which will form the source and drain. Here also you have got two types, PMOS enhancement type. So, in this case there is no flow of current when the gate voltage is 0, but if you apply a negative gate voltage with respect to the source, and if the gate voltage is sufficiently high, it will induce holes in this region, and the holes will act as charge carrier, current carrier between the source and drain, and current can flow between the source and drain. And this is how the PMOS enhancement type transistor is realized, and I have not shown the symbols. Here you can see this is the symbol of a NMOS enhancement type transistors. There are several types, different types of symbols used in the literature, but this is the most commonly used symbol of NMOS enhancement type transistor. Similarly, this is the most commonly used symbol of NMOS depletion type transistor, and then this is the most commonly used symbol of PMOS enhancement type transistor. Then the fourth type of NMOS transistor, that is your PMOS depletion type. In this case, just like the NMOS depletion type, the holes are implanted in this region to create to have channel even when the gate voltage is 0, and then you can apply a positive voltage to the gate to gradually reduce the number of charge carriers in this channel region, and you can in this way you can control the flow of current. So, you can have PMOS depletion type transistor. So, you can see you can have 4 different types of transistor using MOS technology: NMOS enhancement type, NMOS depletion type, PMOS enhancement type, and PMOS depletion type. Now, at this point I should tell you about another important point. You can see in this particular case the current flow takes place by controlling only one form of charge carrier. That means, either you are controlling the electrons, electron is taking part in the flow of current, or holes are taking part in the flow of current. That means, in case of NMOS transistors, the electrons are taking part in the flow of current. On the other hand, in PMOS transistors, the holes are taking part in the flow of current, and that is the reason why MOS devices are known as unipolar devices, in contrast to bipolar devices. Those bipolar devices, those are realized by using, say, junction transistors, for example. Those are bipolar devices because the current flow take place current flow can take place, and where both electrons and holes take part. That means, current flow occurs because of electron hole recombination, that does not occur in case of MOS devices, and that is the reason why MOS devices are known as unipolar devices. Okay. Okay. So, now let us switch gear and let us have discussion on fabrication steps of CMOS transistors. So, we have seen different types of MOS transistor structures. How do you really fabricate them? This is very interesting, and obviously, we cannot really devote much time on it, but remaining part of this lecture I shall devote to fabrication steps of CMOS transistors. So, as I have mentioned, the first step is the realization or creation of a wafer. So, wafer is the material which is also called substrate, on which the VLSI circuits are fabricated. How is it realized? So, what is being done? The purified silicon is held in molten state at about 1500 degree centigrade, as you can see in this cubicle, the crucible. In this crucible, the silicon is kept in molten form, and it is in very highly purified form. How the purification is done, that I have not discussed, but I have already mentioned that by reacting with carbon you can create highly purified form of silicon. So, which is kept in molten form. So, this is the melted silicon at 1500 degree centigrade. And now, what you do, a seed crystal is slowly withdrawn after bringing in contact with the molten silicon. So, here is a seed crystal which is slightly dipped in this molten silicon, then it is gradually withdrawn very slowly. As it is gradually withdrawn, the molten silicon comes in contact with that, and it gets attached to this seed and takes the crystalline form, and as a result, as you gradually withdraw it from the molten silicon, an ingot in this form is created. In addition to this, whenever you do the withdrawal, that time you usually insert some dopant gas inside this chamber. What is the purpose of this dopant gas? As I mentioned, whenever you do the fabrication, the wafer has to be either slightly doped, lightly doped p type or n type. How do you really get this lightly doped p type or lightly doped n type? This is done at this step. That means, dopant of suitable type is passed through this chamber. As you can see, it is introduced here and is coming out from here. So, it is introduced in this chamber, and as a consequence, the ingot that you get is essentially lightly doped p type or n type. It can be either way, it can be done in any one of the two ways. Then after the withdrawal of the seed, an ingot of several centimeters long, 3 to 4 centimeters long and 8 to 10 centimeter in diameter is obtained. Then this ingot is sliced. You can see this is sliced. So, this forms the wafer. So, after slicing this ingot, we get a number of wafers, and the wafer is the base material that is being used for the purpose of fabrication. Then you have to follow a number of steps for the purpose of fabrication of MOS transistor. So, you start with blank wafer, build inverter form from the bottom up. So, we shall show how the inverter can be realized, but you can create more complicated circuit, but here I shall show the formation of an inverter, simple inverter. So, first step will be to form a N-well. So, the most common type is N-well. So, you have started with a p type substrate, and as you know, on a p type substrate you can realize NMOS transistors. depletion type or enhancement type, but CMOS will require both NMOS and CMOS. As I have told, you can have 4 different types of transistors, then CMOS, which stands for complementary MOS, requires 2 types of transistors, one p type transistor, another is n type transistor. For example, a simple inverter will require a p type. Here it is, from the symbol it is very clear that it is a p type enhancement type transistor. You will also require a n type NMOS transistor. So, these two together will form an inverter. So, here you will apply VDD, here you will apply ground, and then you will apply the input here, you will take the output from here. So, you can see a complementary MOS circuit requires 2 types of transistor, two complementary types of transistor. One is PMOS, which acts as pull off network, and the NMOS transistor will act as pull down network. So, here it is a very simplified form of circuit, that is your inverter. You can create very complex circuit, and in that case the generalized structure will be like this. You will have a PMOS network, and you will have another network, NMOS network, and you will apply inputs to both PMOS and NMOS network, and it will take the output from here. So, here is the various inputs, and here is your output, and of course, this PMOS network is connected to VDD ground, and NMOS network is connected to ground and PMOS network is connected to supply voltage VDD. So, this is the complementary CMOS. So, we shall see the fabrication of this inverter, how it is being done. So, first thing to be done is to form an N-well. Why do you require an N-well? Because you will require a PMOS transistor as well for the realization of CMOS circuit. And these are the steps: cover wafer with protective layer of silicon dioxide, then remove layer where N-well should be built. So, this will require 2 steps: cover wafer with protective layer of silicon dioxide. How it can be done? That can be done by a process known as oxidation. Oxidation can be done by hitting this wafer, this substrate, in a chamber like this one, hitting chamber like this one, and then by passing either oxygen or water vapor. So, whenever you are passing oxygen, then it is called dry oxidation, then thin film of silicon dioxide is created. On the other hand, whenever you will be passing passing the water vapor, then thick form of silicon dioxide will be deposited, but its quality will not be very good. It will be little porous type, and it is called thick oxide silicon dioxide. So, you can use either oxygen or water vapor for the purpose of in the oxidation process, and to realize the silicon dioxide layer on top of this substrate. Then remove the layer where N-well should be built. This removal of N-well from the removal of silicon dioxide where N-well should be formed requires a photolithographic process. And then you will implement or diffuse N dopants into exposed wafer, and then you will strip off silicon dioxide. So, you can see you are starting with substrate, then you are growing silicon dioxide on top of the silicon wafer. How it is being done? 900 to 1200 degree centigrade, it is heated and with either water vapor or oxygen in the oxidation furnace, as I have already told. And after that, you do the photolithographic process, that means you deposit photographic emulsion photoresist on top of the silicon dioxide, and then it is spread uniformly by spinning it at little high speed. Then you expose it to light with the help of a mask. So, you require a mask, and this portion is not exposed, as you can see, and then after this portion is not exposed. So, this photoresist can be easily removed from here, and after that by a process known as etching, the silicon dioxide will be removed, H oxide with hydrofluoric acid. So, by reacting with this hydrofluoric acid, this silicon dioxide is removed. So, you have now exposed substrate here, and actually this etching process, you are using an chemical such that it reacts only with the silicon dioxide, not with the silicon. So, only at X oxide when resist has been exposed. So, this portion is silicon dioxide is removed, but not the top portion. Then of course, you will remove the strip of the remaining photoresist, use mixture of acids called Piranha H. So, this is another etching process where you have removed this photoresist from the top of the silicon dioxide layer. Then necessary to resist okay. So, it is necessary to, so resist does not melt in the next step. Then what will you do? You will form the N-well is formed with diffusion or ion implantation. As I told, there are two ways of realizing diffusion region. One is you can again put that wafer in a chamber, and you can pass suitable dopant through that chamber, and it is heated at a very high temperature, and after some time you have to give suitable time, time of suitable duration, such that the dopants can penetrate up to certain layer, and after that you have to do what is known as drive-in process. You have to simply heat it up for certain duration, so that the dopants can get stabilized and gets uniformly distributed within that certain region. So, these are the two steps: place wafer in furnace with arsenic gas, this is the dopant used for this purpose, for the creation of N-well, and heat until arsenic atoms diffuse into exposed silicon. This is the drive-in process. Another alternative, as I told, is ion implantation. Either of the two can be used. Blast wafer with beam of arsenic ions. Ions blocked by silicon dioxide only enter exposed area. That means, here this silicon dioxide is now acting as a kind of protecting layer. So, only this part will have the diffusion, and the other part will not have the diffusion. That means, the arsenic ions will be able to pass through this exposed area, but not through the silicon dioxide layer. Okay. So, this is how the N-well is formed. So, you have got lightly doped area of p type and lightly doped area of n type. So, where you can create two different types of transistors. So, now you have the substrate with N-well. So, strip off the remaining oxide using hydrofluoric acid, then back to bare wafer with N-well. So, this is what is being shown in this diagram. So, subsequent steps involve similar series of steps to define areas where transistors are to be formed. So, formation of N-well by ion implantation, followed by drive-in step, as I have already told. This step I have already discussed. This is done by using mask 1. So, this is the mask 1, this is the mask 1. And coming to the second step, which requires formation of polysilicon layer. So, deposit very thin layer of gate oxide. So, first step is very thin layer of silicon dioxide is deposited, again by the that dry oxidation process. As I told, it will be heated in a furnace and oxygen will pass through the chamber, and very thin silicon dioxide layer will be formed. So, this is what is being done to create the thin oxide layer, and then on top of that you will deposit polysilicon layer, and polysilicon layer is deposited by using a technique known as chemical vapor deposition or CVD on top of this silicon dioxide layer. So, for this purpose what you have to do, you have to place wafer in a furnace with silane gas, forms many small crystals like called polycrystal polysilicon polycrystalline layers, and heavily doped to be good conductor. Since this is heavily doped, so it will form a good conductor, because this will be used for the purpose of interconnection. So, this polysilicon must be a good conductor, relatively good conductor, because it will be used as a interconnection layer to connect different parts of the circuit. Okay. So, this is what another mask is used for the purpose of creating that patterned polysilicon layer. So, use the same photolithographic process to pattern polysilicon. So, earlier for the polysilicon was deposited on the entire surface. Now, you have to create a patterned layer with the help of this mask called mask 3. So, formation of patterned polysilicon regions, and you can see only polysilicon is present in these layers, and from other parts of the substrate polysilicon has been removed. That means, only where transistors are to be formed, there the polysilicon is deposited. So, it is removed from the remaining portion. So, you can see here essentially that gate has been formed, gate portion. So, this is the gate of the NMOS transistor, this is the gate of the PMOS transistor. So, here you have got thin oxide layer and the polysilicon layer, here also thin oxide layer and polysilicon layer. Only difference is here you have got the lightly doped p type substrate, and here you have got lightly doped n type region within the N-well. Okay. Now, what you have to do, you have to create diffusion, you have to create those source and drain regions. So, you have to use oxide and masking to expose where n plus dopant should be diffused or implanted. So, either you will use diffusion process or ion implantation to realize those source and drain regions. So, N diffusion forms NMOS source drain and N-well contact, and formation of N diffusion is done with the help of an N plus mask, which is in effect ended with a mask 4. So, you have got another mask called mask 4 to realize, to define those those source and drains of the NMOS transistors. So, pattern oxide with form N plus region. So, this is the mask of the N diffusion, and this is self anion process where gate blocks the diffusion. So, here you can see this portion there will be no diffusion, and the polysilicon and thin silicon dioxide will protect the the channel region, where channel region will be formed, and only these two areas will be will have the source and drain regions, heavily doped regions, when you carry out those diffusion or ion implantation. So, now you have done that N plus diffusion. So, as I told, historically dopants were diffused by the diffusion process, but nowadays ion implantation is the technique which is commonly used because of its high accuracy. Diffusion, whenever you do the diffusion, then these regions are not very accurately defined. On the other hand, by using, because these lines will not be straight lines, so it will be somewhat like this, somewhat like this, but whenever you do by using ion implantation, then you can then create those N plus regions very nicely. So, you can see 3 N plus regions have been created, source and drain. Another is N-well contact, here N plus region. You have to actually connect this N-well to VDD, and for that purpose an N plus region is created here. So, these three are created by this N plus diffusion. Then you have to strip off oxide to complete patterning process. Oxide is removed, which was acting as a protecting layer for the other parts of the substrate. Then you have to do P plus diffusion. So, for the purpose of P plus diffusion, you will require another mask. So, that is your step 5. So, you have to follow the similar steps to form P plus diffusion region. Only difference is you have to use a different kind of dopant type will be different, and formation of N diffusion is done using P plus mask, which is usually a negative form of N plus mask, because as you know, where you will create NMOS transistor, there you will not create P plus transistor. So, just the opposite, that is the reason why these two are of opposite type, a negative of N plus mask. So, essentially to save the cost of making the mask. So, this is how the P plus diffusion is done. As you can see here, P plus diffusion is done in 3 regions. First, the that source and drain region of the PMOS transistor, and also another P plus region is created here to make contact with the P substrate, because you will see later on that this substrate has to be connected to ground. The entire substrate has to be connected to ground, and to make contact with that substrate, this P plus region is created. So, you can see 3 P plus regions are now created, and so you have got a NMOS transistor, a PMOS transistors, in addition to 2 contacts, one for connecting the substrate to ground, another for connecting the N-well to power supply or VDD. Now, you have to make a circuit. So far here you have got 2 transistors, you have to interconnect them to form an inverter, or you have to, and that inverter may be part of a more complicated circuit. So, you can see here you have to now make contacts. So, another mask is required. So, thick silicon dioxide is grown all over, and then contact card definition using another mask 6. So, you will require a separate mask to create contacts. I mean, wherever you have to make contact with other parts of the circuit, mask is created accordingly. So, now you need to wire together the device, that means all these devices are to be wired together using this, and for that purpose you require these contacts. Copper chip with thick field oxide. So, this thick field oxide is created usually by wet oxidation, as I have discussed earlier. Then H oxide, where contact cuts are needed, again by using that photolithographic process you will remove those thick oxide layers from these regions where contacts has to be established, and then for making the contact you have to do, you have to use a metal layer. So, for that purpose entire substrate will be covered with metal, usually aluminum. So, the whole chip then has metal deposited over its surface to its thickness of 1 micron. The metal layer is then patterned by photolithographic process to form interconnection pattern using mask 7. So, you will require another mask to define the interconnection pattern. So, you may have to connect that inverter to another part of the circuit. So, input has to come from one part, output has to go to another part of the circuit. So, that is being defined with the help of this mask 7. So, you can see this is the mask 7 for creating the patterned metal layer. Another step is also necessary, which is known as overglassing. So, overglassing is done by overall passivation layer, and then this mask is required to define the openings for access to bonding pads. So, once the chip is created, you have to take interconnect connections to the outside world, then you have to form a package. So, for that purpose you have to again make holes at the appropriate places, not only for taking interconnection, but also for the purpose of testing. So, to test different parts of the circuit you have to make contacts at different points within the chip. So, that is done in this step, this overglassing step. So, overglassing is done by overall passivation layer, and this mask is required to define the openings to access to bonding pads. So, they will be connected to the bonding pads, and then you will form a package, either dual inline package or some other kind of package, and then it will be available in the market. Before I conclude this part, I think I should tell about another alternative way of realizing CMOS circuits, and that approach is known as silicon on insulator. So, here we have seen that in the conventional approach, which is also known as bulk CMOS. So, here what you are doing, you are starting with a substrate, and then you are creating the N-well, you are creating the NMOS and PMOS transistors. Here is the NMOS transistor, here you are creating the PMOS transistors. This is the channel region. Then you are doing the interconnection, you are taking and you can see this is the, you can say this is the bulk substrate, and in this case this substrate is, entire substrate is connected, because this is the P plus region is created and this is connected to ground, and similarly the entire that this is the well, this is connected to VDD. This is the bulk CMOS. Here this is one approach. Another approach is you will start with the substrate, then you will deposit silicon dioxide layer. So, here is your SiO2. So, this is the insulator, and on top of this you will create those various transistors. That means, you will form a NMOS transistor, you will form a PMOS transistor, then you will do the interconnections and so on. So, you can see this is called silicon on insulator. This is an insulator, and on top of this insulator you are creating different transistors, and then of course, you will be doing interconnections among them. So, you can create N type transistor, you can create P type transistor. Here you are not forming any well, but on a silicon dioxide layer you are forming different types of transistors and interconnecting them, and this is known as silicon on insulator. Or SOI. So, there is clearly there are two different groups. For example, Intel, Texas Instruments, they are following this approach, bulk CMOS approach for realizing VLSI circuits. On the other hand, the SOI approach is being followed by IBM. IBM is using SOI approach for realizing VLSI circuits, and it has been found that this SOI approach has some good features. Bulk CMOS also have some good features. So, that means, these two approaches have their own advantages and disadvantages. Particularly SOI approach has been found to be very suitable for low voltage, and at low voltage it gives you very good quality transistors, but it has other problems. But that means, all I am trying to tell that this bulk CMOS and SOI, these two are two alternative approaches available for the realization of CMOS VLSI circuits, and some fab houses are realizing VLSI circuits using bulk CMOS, and some fab houses like IBM, they are realizing VLSI circuits by following SOI approach. Okay. Coming to the last slide, you have to make a kind of layout. I have simply shown the formation of an inverter. So, and I have shown you will require a number of masks to realize the to create that create different transistors and make the interconnections. So, chips are specified with set of masks. We have seen 8 steps are required and 8 masks are required, and minimum dimension of masks determine transistor size. So, there the masks will be created where you have to, those are nothing but you have to create a kind of pattern, geographic patterns, and they will have some separation, some you have to maintain some width like that, and that will decide the speed, cost and power. And a parameter known as feature size f is used, which is essentially a distance between source and drain, and it is set by the accuracy of the photolithographic technique available on that date. And with the improvement of this photolithographic technique, these dimensions are getting reduced gradually. As you know, earlier you had 500 micron, now you are close to 33 micron, and this is happening because of the advancement of photolithographic and other techniques. So, this minimum width decides the feature size, and feature size improves 30% every 3 years or so. You may have heard of Moore's law. So, Moore's law tells that every 18 months the number of transistors on a wafer will double. How it is happening? The feature size is decreasing, and normalize for feature size when describing design rules. And whenever you are making the pattern, that means the layout, then you have to follow some design rules. These design rules are specified in terms of a parameter known as lambda, and all these rules are expressed in terms of lambda. Lambda is nothing but this feature size by 2. That means, whenever it is a 0.6 micron process, then lambda is equal to 0.3 micron. Okay. So, that means the layout is created by following a number of design rules. Those design rules are specified in terms of lambda. That means, the maximum channel length should be 2 lambda, or I mean minimum channel length should be 2 lambda, like that. Width should be say lambda, and those I am not going into the details of those design rules, but they are specified in terms of lambda. Okay. So, this is how you will be creating layout, and you will realize a complex VLSI circuit. Okay. So, with this we have discussed, to summarize what we have discussed today, we have discussed the the structure of MOS transistors, and we have seen there are 4 different types of transistors possible in MOS: NMOS enhancement type, NMOS depletion type, PMOS enhancement type, and PMOS enhancement type and PMOS depletion type, and you can use them to realize circuits, different types of functional circuits like inverter, NAND gate, NOR gate and other things. And so then we have discussed the fabrication steps, particularly fabrication steps of a CMOS circuit, and we have seen there are 2 basic approaches, that is one is based on that traditional approach, bulk CMOS, another is your silicon on insulator approach. Now, I would like to give you some references. So, this first book by Kang and Kang, CMOS digital integrated circuit, this book gives you the background material that will be required for this course. It discusses in details of CMOS circuits, starting with MOS transistor, MOS inverter, MOS complicated circuits. Similarly, West and Esragian's books also gives you necessary background for CMOS circuits. Then coming to our low power circuits, this book is very good by Bellamour and Elmasri, low power VLSI CMOS circuits. But unfortunately, as you can see, this book was written in 1995, it is little old. And another book is also there by Anant P. Chandrakasan and Robert W. Borderson, low power digital CMOS circuit design, published by Cloar Academic, that also published in 1995. So, these two books are primarily on low power CMOS circuit design, but unfortunately these are not available in Indian edition. So, I requested the library to purchase few copies of these books. These books may be available in the library. Another recent book is a edited version, edited by Christian Pigout, and low power CMOS circuits technology, logic design and CAD tools, and this is a more recent book. However, you will see that major part of my lectures, particularly in the later part, will be based on material taken from papers. I cannot really give you any copies of everything, but later on I shall provide you some of these papers, copies of some of these papers, and lecture notes are also available, but it may not be necessary for you because these lectures will be uploaded in the in our CET website. So, you can access them maybe after 1 or 2 days, and you can go through them again and again if necessary. So, with this we have come to the end of today's lecture. In the next lecture we shall discuss about a model by which you can explain the operation of PMOS transistors, that is known as fluid model, that we shall discuss in the next class. Thank you very much.